Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3.
And in this video, we will talk about
human population in Samoa Island.
And Trapezoidal role.
Now, let us introduce ourselves. My name is Ali.
My name is Iskandar Syaimi.
my name is Ikmal Haris.
My name is Abdul Hafiz.
And my name is Nur Haria.
Now, let's go to the explanation. There are two parts, which is human population and also trapezoidal rule. Now, look at the table of contents of the human population. For the introduction part, we choose Samoa Island because it is interesting for us to explore a country that does not have an advanced technology, a powerful economy, and also a strong military. Starting of the 21st century, most of countries have developed and evolved, so we can get a more accurate data based on their human population at the certain years. So we observe the data from years 2000 until 2019. Okay, the formula used is dP over dt directly proportional with P, or dP over dt is equal to Kp. These are the table of the actual data and also the years. We assign the years from 2000 until 2019 by T, where the T is starting from 0 until 19. So we will get 20 data. From the first part, where dP over dt is equal to Kp, we need to solve this equation by separating both of the variables, where is P and also T. After that, we need to integrate both sides, where at the left side have 1 over P with respect to dP is equal to, on the right side, K with respect to dt. After integrating both sides with respect to each variable, we need to simplify the equations to get the general solutions. After that, we need to substitute each with the initial condition, which is P and also T, and we will get A. After that, we need to search for the K. For this K part, we need to search for all of the K value for each T. So we move to the next slide. This table shows that all of the K by using this formula. After that, we will get the K average by the sum of the total K. We will divide by 90 and we will get the K average. The K average here, we will insert in the formula of the general solutions to get the particular solution. And then we will insert the P for all the data to get the particular solution value for the human population.
Let's move on to the next part, which is the data analysis. As we can see right now, we have transferred our data in the table in the form of graph. This graph is the graph of population of actual population in Samoa against with time. One key point that we can highlight in this population is the highest population of people in Samoa is in the year of 2019, which is 211,905 people. This means by time of year, people in Samoa increase gradually. So the next part of data analysis will show to you guys of the graph of particular solution of population in Samoa against time. This particular solution has been calculated using the formula that have been introduced. This graph shows that population in Samoa increase exponentially. That means over time, people in Samoa increase. On the last part of the data analysis is how did we actually predict the past value and the future value of the people in Samoa. How did we actually use this? We use the formula of the particular solution, which is Pt equal to 184,008 times Vt to the power of 0.006227 times Vt. For the past value, we take the year of 1998 as a sample. So by mean from that, the T value is -2.
From that, we get the value of 181,304.74 and then round it off to get a value of 181,305.
For same goes for the future prediction. We substitute in the particular solution equation. We take example of the sample from year of 231. So the T will be 21. We substitute it.
And we get the value of 214,944.36 and we round it off to get the value of 214,944.
After doing that, at the end of data analysis, we make a percentage of error to find out how did actually the difference that we got from the actual value of the population and different with the we use the formula. We use the formula of percentage of error, that is actual value minus particular solution over actual value times with 100. For the past value, we got the percentage of error which is
0.51%.
And for the present value, we got the percentage of error, which is
0.16.
we also need to find out the percentage of error for all the data that we collected from the year of 2000 until 2019. As a sample, we take the value of population in the year of 2002, which is the T is 2, and substitute it into the percentage of error calculation. And then from that, we got the percentage of error of
0.16%.
this calculation have to make is it what we calculate using the equation sync and link with the actual population in Samoa.
Okay, so now we will be proceeding with discussion. From the analysis, we have obtained an estimate value by applying the Malthusian model. The Samoa Islands population from year 2000 to 2019 are lower than the actual value, with percentage error of 4.14% for the future population and 0.74% for the past population. There are many reasons for the inconsistency in accuracy, and one of them is migration. So many Samoans are moving abroad to the European countries or to the US due to the political issue in their country, reducing the local population. The Malthusian model does not account for real-world factors, resulting in inaccuracy in finding the estimate value. So the second one is natural disaster. The Samoa Islands is prone to natural disasters such as cyclones, tsunamis, and earthquakes. These events can lead to loss of life. In Malthusian model, unpredictable events are not considered, causing a flaw in our estimate value. So the third one is economy factor. In this era, the higher cost of living makes raising children become more expensive, lowering birth rate to a certain level. The parents are likely to do a family planning on how many children they have in order to control their financial situation. So now, in our conclusion, we have achieved task 1's objective on focusing the application of first order of differential equation to our project. By using the approach, we were able to determine the increase in population in Samoa Islands from 2000 to 2019. Other than that, we have calculated the percentage error due to the difference between the estimate and actual values. Based on the result, we determine the causes of the values unfavorable comparisons. We have also identified the real factors that cause inaccuracy in population, such as migration, natural disasters, and economic factor. Overall, the project allows us to apply mathematical techniques, such as the Malthusian model, to solve problems in a realistic manner.
For task 2, we've been given a question to use trapezoidal rule with 7 and 11 sub-interval to find an approximation of integral sign set 8x cubed cos x minus 3dx with the limit from negative 13/10 to 0. And we have to give our final answer to correct 6 decimal places. What is the function of trapezoidal rule? Trapezoidal rule is used to approximate the area under a graph. In order to find the integral for the graph, we first need to find h, which is h equals to in bracket b minus a close bracket over n, and the b value is the upper limit, which is 0, and the a is the lower limit, which is negative 1.3, and n is 7. And after we find h, we can use it to find x. And in order to find x, we first need to put the lower limit and add x subsequently to the next data until our data reach the upper limit. And after we get x, we can find fx. And how to find fx is that we just substitute the x in our equation. And after we get fx, we then need to find the coefficient, which is for the first and last data is 1, and the rest is 2. And after we get the coefficient, the x and fx, we can find the sum of multiplication for coefficient and fx. And in order to find that, we need to multiply coefficient with fx for each data. And after we get x, fx, and h, we can use them into a new formula, which is h over 2 times with the sum of multiplication of coefficient and fx times with h. And after that, we will get the integral.
So after applying the trapezoidal rule in the Excel, we found that with 7 steps interval, the estimate area under the curve is 1.778703, while with 7 steps interval is 1.779328. Even though the difference is small, it shows that using more steps intervals gives a more accurate approximate area under the curve. Now take a look of the graphs from Desmos. Figure 2.3 shows that the graph with 7 steps interval, while figure 2.4 shows the graph with 11 steps intervals. Both graphs show the same interval, which from -30/10 to 0, but the number of trapeziums are different. When more trapeziums appear in the graph, like in figure 2.4, each one of the trapeziums become narrower, which allow the trapeziums to follow the shapes of the curves. This will reduce the space between the top of each trapezium and the curve, especially in the curves that bends more. And that's why the estimate area under the graph of figure 2.4 is more accurate compared to 2.3. So overall, a higher number of trapeziums leads to a better and more precise approximation of the actual area under the curve.
So that is the end of our presentation. Thank you for watching.